Hello everyone, and in this video I'm going to discuss about the electron, which is one of the three subatomic particles that compose the atoms. If you can remember, we discussed in a previous video about Dalton's atomic theory, Dalton's atomic theory, and in that Dalton explained that the smallest unit of matter is the atom, and he explained that these atoms cannot be further subdivided into any smaller or any finer particles. But later scientists discovered that even atoms are composed of even finer particles known as subatomic particles, and these are electrons, protons, and neutrons. Out of these three, electrons were the first to be discovered, and these were discovered thanks to a glass tube called the Crookes tube. Crookes tube, which was of course discovered by William Crookes. William Crookes. The term electron, actually, this term electron was actually coined by another scientist named Johnston Stoney. Johnston G. Stoney. He said that the fundamental unit of electricity is the electron. The fundamental unit of electricity is the electron. This is what Johnston Stoney said, but actually he did not have any experimental data to prove his idea. The presence of electrons was actually discovered by some other scientists later using the Crookes tube. A Crookes tube is a glass tube, which is connected to a vacuum pump. Thereby we can create a vacuum inside this glass tube. Now also this glass tube consisted of a couple of electrodes on either sides. One of them was called as the cathode and was connected to the negative terminal of a voltage, and the other electrode was called as the anode, and it was connected to the positive terminal of the power source. The power source was a DC voltage, a high DC voltage, which was around 10 to 20 kilovolts, and a very low pressure was created inside this glass tube, which was approximately 0.0001 mercury millimeters. So what they discovered was that under such low pressures, if we provide a huge voltage like 10 to 20 kilovolts, what happens is some form of radiation was emitting from this negative electrode and was traveling towards the positive electrode. And this radiation was called as cathode rays, as they seem to be emerging from the cathode. These cathode rays were actually invisible to the naked eye, but the presence of them was discovered due to them being capable of creating glow effects, glow or fluorescence. in the low pressure gases inside. Hopefully you are familiar with how we denote a magnetic field on paper, how we draw a magnetic field on paper. How do we represent a magnetic field on paper which has a direction from left to right? Left to right. That's very easy. We use a set of parallel arrows. These should be actually equally spaced for it to be correct. And we point them to the right because we need the direction of the magnetic field to be from left to right. What is actually happening here is the magnetic field lines are running from north to south, which is left to right. That is the direction of a magnetic field, north to south. And if we want to represent a magnetic field that is that has a direction from right to left, we do the same thing, this time changing the direction of the arrowhead like this. Now it's right to left. North is on this side and south on this side. And if we want to have a magnetic field from top to bottom on our screen, we can do it like this. Just put the arrowheads at the bottom of the line, bottom of the lines. Now we have north, south, top to bottom magnetic field. Similarly, we can have a bottom to top magnetic field by having arrowheads to the top of these lines. Now the south is here, north is here. Now we have magnetic fields in 4 directions. But what if we have to represent a magnetic field that is going into the screen or coming out of the screen? What can we do about that? How can we represent such a magnetic field? Now, in such a situation, if the magnetic field is going into the screen, then we can represent such a magnetic field as a set of crosses. Why we are using crosses is because if we consider a real arrow, one end of the arrow is pointy and the other end has something like this, feathers. If we look at these feathers straight on like this, you will see something like this, like a cross, and the arrow is not visible to the eye. Similarly, if you place your eye like this and look at this arrow, you will see a point, like a dot. You will see the point of this arrow. Therefore, when we represent a magnetic field that goes into the paper, we represent it as a set of crosses. And similarly, if we want to represent a magnetic field that is coming out of the paper, then we represent that as a set of dots. They should be equally spaced. Mine are not, but these should be equally spaced. Now, why I am discussing these things is I need to explain the movement of a charged particle through a magnetic field. To describe that, we need to know these representations. Now let's consider a magnetic field which is running into, which has the direction from outside to the inside of the paper or the display. We can denote the magnetic field like this. And now, if we allow a charged particle, a positively charged particle, to pass through this magnetic field, according to Fleming's left-hand rule, there is a force acting on this particle from bottom to top due to this magnetic field. As a result of this magnetic force, this positive charge will change its path of movement like this. It will curve upwards, and once it exits the magnetic field, it will again follow a straight path. Similarly, if you allow a negatively charged particle to pass through this magnetic field, it will have a force acting on it to the opposite direction according to Fleming's left hand rule, and it will change its path like this, and once it exits the magnetic field, it will keep following a straight path. What if we reverse the direction of the magnetic field? Let's consider such a situation as well. If we have a magnetic field that is coming out of the paper or coming out of the screen in this situation, you are looking at a screen. Now what will happen to a positively charged particle? If this particle tries to go through this magnetic field, now the direction of the magnetic field is reversed. As a result of that, this particle will have a force downwards, top to bottom, and that force will cause this particle to change its path, and once it exits the magnetic field, it will keep following a straight path. And again, if we allow a negatively charged particle to pass through this magnetic field, it will not follow this straight path, but it will begin to curve, and once it's out of the magnetic field, it will keep following a straight path. This time the force on the negative charge is bottom to top. The significance of this phenomenon is that scientists used magnets to create magnetic fields across the Crookes tube, so that allowing cathode rays to pass through the magnetic field. Now what they observed was that cathode rays showed a similar deviation of their path as done by negatively charged particles. So cathode rays, instead of going straight through the magnetic field, they were deflected just like an electron would do, like this. Did not pass through as straight lines. Instead, they deflected like a negatively charged particle would do, not to the other direction, not this way, not to the direction to which a positively charged particle would deviate its path. Now this helped scientists to conclude that cathode rays are actually charged, and specifically they are negatively charged. The reason is that if the path of some moving thing to be deviated or changed by a magnetic field, then that moving thing should have a charge. If a thing, let's say a particle, if a particle is to deviate its path of movement through a magnetic field, then that particle must have a charge. It could be positive, could be negative, that doesn't matter. And also by the direction of the movement, by the direction of the change of path, we can conclude whether it's a positive charge or a negative charge. Now these observations led to the conclusion that cathode rays are charged, and they are specifically negatively charged. Another experiment conducted using a cathode ray tube or a Crookes tube is that they obstructed the path of the cathode rays. We draw a few cathode rays. They obstructed the path of these cathode rays with an object. maybe let's say an object having the shape of a cross, like this. What happens if we place this cross inside of this tube, like so? This cross, preferably a metal cross, this cross will block some of these cathode rays and thereby creating a shadow behind it. It casts a shadow behind it. A shadow is casted onto the wall of the glass tube. We can also completely block the path, thereby completely darkening the other side of the cathode ray tube. What this means is that cathode rays travel in straight lines. If we can take this shadow onto a screen, we can see that this shadow is quite sharp, with sharp edges and not blurry edges, which proves that cathode rays are traveling in straight paths, straight paths, straight paths, and these straight paths are deflected by using a magnetic field. Furthermore, scientists used electric fields to study the changes that occur in cathode rays due to the presence of an electric field. Let me draw a cathode tube again. Now this time they applied an external electric field across this Crookes tube, like this, plus minus, positive negative. And in this kind of a situation, they found that cathode rays, instead of going towards the anode, their path bends towards the positive side of the electric field. Now this also confirmed that cathode rays have a negative charge. Now at this time, some people believe that these cathode rays are beams of particles, but some others believe that these should be some sort of waves. To clarify this, scientists used a pedal wheel inside the Crookes tube. Let me draw it. They used a pedal wheel, something like a fan, which has blades and which can be rotated using flowing air. If a fan is rotated using electricity, the fan gives out moving air. Similarly, if moving air hits a stationary fan, then the fan rotates because air particles being hit on the fan blades. Similarly, if you use a similar small fan, this should be actually a lightweight fan, or even a pedal wheel can be used. Pedal wheel like that you see in older boats. In old boats, you might have seen something like this, which has pedals, and this can be rotated mechanically to generate a force to move the boat forward. And something like this can also be used in the Crookes tube, a lightweight, smaller version, not a big one you use in a boat. And what happens is, when this Crookes tube is activated, when you switch on the Crookes tube, these generating cathode rays will hit the fan, hit the blades of this fan, or if we use a pedal wheel, the blades of the pedal wheel are hit by these rays, and this causes the fan blades or the pedal wheel blades to rotate in the same direction as if it would as if it was hit by moving air. Now, if you shine light on a fan, will those blades rotate? The answer is no. So therefore, scientists concluded that these should be beams of particles. Beams of particles. These should be beams of particles, not waves. I told you that some scientists were arguing that these were waves, and some others were arguing that these were beams of some sort of particles. But due to this observation, it proves that cathode rays are actually moving beams of particles, not actually any sort of waves. So these experimental evidences show few properties of cathode rays, properties of cathode rays, such as they travel in straight lines, straight paths. They travel in straight paths. They are beams of particles, particle beams, not waves. Then also these show that they have a negative charge. These were the conclusions they were able to gather by doing different experiments using the Crookes tube. And also they did some other adjustments, other changes to the Crookes tube as well, such as changing the metal used to make this cathode material. They use different metals as the cathode material, and they found out no difference in the emitting cathode rays. They were all similar. And also they used different gases in this tube, different gases under low pressure, of course. But even using different gases, they didn't find any differences between the generated cathode rays. Now these two observations, that means the observation of not seeing any difference between the generated cathode rays by changing the gases inside, and also by changing the cathode material. This observation led to the conclusion that these particle waves, or these particle beams, which are cathode rays, were fundamental to all the metals, all the material, and it does not depend on the type of material we use. J.J. Thomson, who was a British scientist, also conducted some experiments with these types of Crookes tubes, and he found out that the charge to mass ratio of these cathode ray particles, you can denote it as Q over M, Q for charge and M for mass. He found this is equal to 1.76 into 10 to the 8 coulombs per gram. J.J. Thomson also introduced a new model for the atom, a new atomic model, which is famously known as the plum pudding, the plum pudding model. J.J. Thomson said that the atom is something like a pudding in which plums are embedded in it. So these plums can come out and also go back in to the pudding. We can pick out plums and we can also insert the plums into the pudding. Now these plums were electrons and the pudding was a positive mass. And according to Thomson's plum pudding model, negatively charged electrons were embedded in a positively charged mass. Positively charged mass. And he explained using this model that these electrons are the ones which are jumping out of this cathode as a result of the externally applied high electric field, and these electrons travel to the anode, which is positively charged, as beams of particles. And this was J.J. Thomson's atomic model, which is called as the plum pudding model. I should mention another important name here. That's Robert Millikan. He found out the charge of an electron in coulombs, charge of an electron to be 1.602 into 10 to the negative 19 coulombs. He did a famous experiment known as the oil drop experiment. Using that experiment, he found out the charge of an electron to be 1.602 into 10 to the negative 19 coulombs. Now using this value, charge of an electron, and also by using this value, which is the charge over mass ratio, one can find the mass of an electron, the mass of an electron, and if you simplify this, and you will get 9.10 into 9.1 into 10 to the negative 28 grams. So this is the mass of an electron in grams, and they already knew the mass of a hydrogen atom by this time. So they found out that the mass of this electron thing is 1 over 1837. Let me write it here. 1 over 1837th of the mass of a hydrogen atom, of the mass of a hydrogen atom. So this fact that the mass of an electron is 1 over 1837th of the mass of a hydrogen atom confirmed that there were particles smaller than an atom, because hydrogen atom already is the smallest atom, but the electron has an even smaller mass. Therefore it concluded that Dalton's atomic theory's first postulate was actually not correct. So that's all I'm going to discuss about in this video. Maybe these videos feel like too lengthy and too descriptive for somebody, but my aim is to explain everything as in as much detail as possible, so that everyone can gain from this. So thank you very much for sticking with the channel, and please subscribe and like this video. Also click the bell icon so that you get notified when I release my next video. So until I see you in the next video, happy learning.